Venus, our neighboring planet, exhibits a unique atmospheric phenomenon known as superrotation. Unlike Earth, where the atmosphere circulates relatively in line with the planet's rotation, Venus' atmosphere speeds around the planet much faster than Venus itself rotates. Specifically, while Venus completes one rotation on its axis in 243 Earth days, its atmosphere circles the planet in approximately 4 Earth days. This superrotation means that Venus' atmosphere moves at speeds up to 60 times faster than the planet's surface. The cause of this phenomenon is not fully understood but is believed to involve complex interactions between solar radiation, atmospheric chemistry, and the planet's slow rotation. These factors contribute to a massive difference in temperature and pressure that drives the high-speed winds encircling Venus. Studying Venus' superrotating atmosphere offers insights into other planetary bodies with similar characteristics but also helps scientists understand atmospheric dynamics.
Valles Marineris is one of the most spectacular features of the Martian surface, often likened to the Grand Canyon on Earth, but on a vastly larger scale. This enormous canyon system is located near the equator of Mars, just east of the Tharsis region, a vast upland area that is home to some of the largest volcanoes in the solar system. Valles Marineris is colossal. Stretching over 4,000 kilometers, about 2,500 miles in length, it dwarfs the Grand Canyon in both length and depth. Its width ranges up to approximately 200 kilometers, about 124 miles, and it reaches depths of up to 7 kilometers, about 4.3 miles. For comparison, the Grand Canyon is about 446 kilometers long, up to 29 kilometers wide, and 1.6 kilometers deep. Although no missions have yet landed in Valles Marineris, it has been extensively imaged from orbit by various missions. Jupiter's magnetic field captures charged particles, including electrons and protons, from the solar wind as well as from the volcanic eruptions on Io, one of its moons. Io is the most volcanically active body in the solar system, and its eruptions spew vast amounts of material, including sulfur dioxide gas, into space. This material gets ionized and becomes trapped by Jupiter's magnetic field, contributing to a vast magnetosphere filled with charged particles. These trapped particles form radiation belts around Jupiter, similar to Earth's Van Allen belts but far more intense. The magnetic field accelerates these particles to high speeds, creating a radiation environment that can be more than 1,000 times stronger than Earth's radiation belts. The intense radiation belts extend up to several million kilometers from Jupiter, encompassing the orbits of its innermost moons. The concept of diamond rain on Saturn is a hypothesis drawn from the understanding of the planet's atmospheric conditions. It begins with methane, a common gas in Saturn's atmosphere, which can be broken down by lightning storms into carbon and hydrogen. The carbon from this process may initially cluster into forms like soot or graphite. As these carbon particles journey deeper into Saturn's atmosphere, they encounter increasingly extreme conditions. Specifically, at depths where the pressure is more than 1,000,000 times that of Earth's atmosphere and temperatures reach several thousands of degrees Celsius, it's theorized that these carbon forms undergo a remarkable transformation into diamond. These newly formed diamonds aren't destined to remain solid forever. Continuing their descent, they might eventually reach layers where the heat and pressure are so intense that the diamonds could dissolve into a liquid carbon state. Uranus's magnetic field is tilted at a staggering 59 degrees from its rotational axis and is offset from the planet's center. This orientation results in a magnetic field that is drastically lopsided, leading to a magnetosphere where magnetic reconnection events, a process where magnetic field lines from different magnetic domains are forced together and realign, occur far more frequently than on other planets. This magnetic alignment is believed to be the result of Uranus's internal structure, which possibly includes a relatively thin shell of highly conductive fluid, like water mixed with ammonia and methane ices, surrounding a rocky core. The rapid rotation of this conductive layer generates Uranus's magnetic field. This action, combined with the planet's severe axial tilt of 97.77 degrees, results in extreme seasonal variations in its magnetosphere, unlike anything observed in the rest of the solar system. Unlike the full rings found around other gas giants, Neptune's rings are incomplete and clumpy, forming distinct arcs. This peculiar structure is not fully understood but is thought to be due to the gravitational interaction with Neptune's moons. Neptune boasts the fastest winds in the solar system, with speeds reaching up to 2,400 kilometers per hour. These winds move at supersonic speeds, far exceeding any storm winds found on Earth, and their exact cause is still a subject of research. Neptune has 14 known moons, with Triton being the largest and most unusual. Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, suggesting it was captured by Neptune's gravity. Moreover, Triton is geologically active, with Voyager 2 observing geysers shooting material up to 8 kilometers, 5 miles, into the Moon's thin atmosphere. Pluto, a dwarf planet nestled in the distant reaches of our solar system, boasts a surprisingly complex and dynamic environment, challenging long-held notions about celestial bodies so far from the Sun. One of its most captivating features is its complex seasonal variations. Unlike anything seen on the more proximate planets, Pluto's seasons are dictated by its highly elliptical orbit, which brings it significantly closer to and farther from the Sun over its 248-year-long orbit. This extreme variation, combined with Pluto's axial tilt of about 120 degrees, results in dramatic changes in its atmosphere. At its most distant, Pluto's thin atmosphere, composed primarily of nitrogen, methane, and carbon monoxide, freezes out and falls as snow onto its surface. As it approaches closer to the Sun, the atmosphere thaws and reforms. Gula Mons is a significant volcanic feature located on Venus, one of the many volcanic mountains that dot the planet's surface, illustrating its geologically active nature. Venus, shrouded in thick clouds of sulfuric acid, has a surface that has been extensively mapped by radar imaging, primarily by missions such as NASA's Magellan orbiter in the early 1990s. These radar images have revealed a landscape dominated by volcanic features, including vast plains covered in lava flows, volcanic domes, and numerous mountains believed to be volcanoes, among which Gula Mons stands out. Gula Mons rises about 3 kilometers, nearly 2 miles above the surrounding plains, making it one of the taller mountains on Venus. It is located in a region known as Isla Regio, near Venus's equator. The mountain spans approximately 250 kilometers, about 155 miles in diameter.
I'm floating through the cosmic sea, lost in a galaxy unknown to me. Neon lights, they flicker and glow in this strange world I call my own. Waves of sound, they echo in my ears as I navigate through my fears. A distant star shines in the night, guiding me towards a new insight. In this exoplanet, searching for a place to call my own, lost in this vast unknown.
In November 2023, astronomers made a groundbreaking discovery using NASA's Chandra X-ray Observatory and the James Webb Space Telescope. They identified the most distant black hole observed in X-rays, located in a galaxy named UHZ-1. This black hole is notable not just for its distance, 13.2 billion light-years away, a mere 470 million years after the Big Bang, when the universe was only 3% of its current age, but also for its massive size at such an early stage. It weighs between 10 and 100 million suns, comparable to the mass of all the stars in its galaxy, challenging previous notions about how supermassive black holes form and grow. This discovery was facilitated by gravitational lensing from the galaxy cluster Abell 2744, which magnified the light from UHZ-1, allowing the telescopes to detect it. Imagine gazing up at the night sky and suddenly, a new bright light pierces the darkness, visible to your naked eye. This could be a supernova or kilonova, explosive events signaling the death of stars or the collision of neutron stars, respectively. These cosmic fireworks are so powerful they can briefly outshine entire galaxies, making them visible from millions of light-years away. Yet, despite our technological advancements, predicting the exact moment one of these awe-inspiring events will occur remains one of astronomy's greatest challenges. The universe keeps its schedule secret, and while telescopes like NASA's James Webb and the Chandra X-ray Observatory scan the heavens, capturing fleeting moments of cosmic history, we wait in anticipation. One day we might just look up and witness a celestial spectacle, a once-in-a-lifetime light show, reminding us of the universe's vastness and the mysteries it holds, all without a moment's notice.